Hi everyone, welcome to the post-contest discussion of TLE Eliminators. I am Soumojit Chatterjee, and today we will discuss the first four problems from A till D of today's Codeforces contest. So I hope you all had a great contest. Before starting any discussion, I would like to confirm whether my screen and my voice is clearly audible and visible or not. Okay, great. So guys, I would request you to be a bit interactive on chat, and you all have permissions to unmute your mic. So at any time, if you feel that, okay, something is not clear, or maybe you require some more extra discussion or a dry run on some question, please feel free to ask, or at least write in chats so that I can confirm once. Okay, so let's start. Before starting once, I would like to ask you all, like, how did you feel? How was the difficulty of today's contest? Like, was it on the easier side or on the difficult side, or was it something like how a usual CF Div 2 is? So guys, okay, great. Harsh says moderate. So probably, uh, okay. So if you ask me, I felt that today's contest was a bit on the difficult side. But okay, difficulty is relative. It depends on a lot of different factors, like whether you are familiar with the topics asked in today's contest or not. Uh, Before making any further delay, let's start with the first problem of the contest, problem A. So let's start. So let me read the problem statement first. The question says two frogs, and this is what the question is. It says that there are n lily pads arranged in a row, numbered from 1 to n from left to right. Okay, great. Alice and Bob are frogs initially positioned on distinct lily pads A and B respectively, and they take turns jumping, starting with Alice. Okay. During a frog's turn, it can jump either one space to the left or one space to the right as long as the destination lily pad exists. So, for example, on first turn, Alice can jump to either lily pad A minus 1 or A plus 1, provided that these lily pads are within bounds. It is important to note that each frog must jump during its turn and it cannot remain on the same lily pad. Great enough. However, there are some restrictions. What are the restrictions? The first one is that the two frogs cannot occupy the same lily pad. This means that Alice cannot jump to a lily pad that Bob is currently occupying and vice versa. Okay. The second part is that if a frog cannot make a valid jump on its turn, it loses the game. As a result, the other frog wins. Determine whether Alice can guarantee a win, assuming that both players play optimally. It can be proven that the game will end after a finite number of moves if both players play optimally. Okay, great enough. So let's begin. In this problem, there were some very important things to note down. But before that, let me explain the problem statement once. So the input to the problem is, two integers a and b. Just a second. Okay, it also gives an n. Great enough. So it also gives an n. So n represents the number of lily pads. That's clear. So n is the number of lily pads. Let me call it number of positions. A is Alice's position and B is Bob's position. So I hope that is clear. A is Alice and B is Bob. What does the question says? The question says that you have n lily pads. So you have 1 till n lily pads. And initially Alice is standing at some of the positions. So suppose this is where Alice is standing at the position A. And suppose Bob is standing at some position B. So this is Bob standing at some position B. Okay, great. At one step, Alice can move anywhere to the left or the right. Similarly, at one step, Bob can move anywhere from the left to the right. They make moves alternately. That means first Alice makes a move, then Bob makes a move, then again Alice makes a move, and it continues. The question specifically mentions that, okay, if you are standing at, say, this part, at the leftmost corner of the cells, so if you are standing at position number 1, so suppose this is where Alice is standing, then it can only move to the right. It cannot move to the left because there is no valid index here. Same goes with Bob. Now, what does the question asks? The question asks for this. So this is what the question says. Okay, let me write it down. The question says, can Alice force to win the game? So can Alice play in such a way that whatever Bob does, Alice always wins? Does that happen? So this is what the question asks. Either you have to print a yes or a no. So is the problem statement clear? Someone who is confused with the problem? Guys, confirm a bit. Like if it's not clear, then please write a yes. Okay, great. So the problem is clear. So now, there are a few important observations to make. So let us try with some easy cases, and then we will try to build on a difficult cases one by one. So this is the first case. So I will just enlist the cases, and I will expect that you would be able to understand or reason about why should the answer be this. So suppose n is 2. That means I just have 2 lily pads. So I have 2 lily pads, and Alice must be standing at one of them, and Bob must be standing at the other, right? So if this happens, then what should be the answer? Like, is the answer something very obvious in this case? What should be the answer? Anyone in the chat? Okay, great. So here the answer should be no, right? Yeah, Anand said Bob, and that is what the answer should be no here. So can Alice force a win? So the question is, can Alice force to win the game? No, Alice can't force to win the game. Why so? Because Alice is here, right? In the first move only, Alice cannot make a move because Alice cannot go to the left. There is no valid position. Alice cannot go to the right as well because Bob is already standing there. So that means Alice cannot make a move. So it is forced to lose the game if n equal to 2. The same happens when you switch the positions. So suppose you switch the positions, and suppose here is where Bob is standing and here is where Alice is standing. I hope it is clear that it is obvious that it is the same case. Alice cannot go to the right here because there is no invalid position. It cannot go to the left because Bob is already standing there. So Alice will definitely lose the game, and the answer is no. Great. Now let me talk about two more cases which is something very obvious. So this is the second case. What if A equals 1 and B equals 2? Or, or what if A equals n and B equals n minus 1? What should be the answer in these two cases? Any idea? Great. Even these are just corner cases. Even in this case, the answer should be no, right? Because what do these cases signify? So these cases basically say that, okay, I have a large, I have lot of cells. Just a second. Yeah, so this signifies that, okay, I have multiple lily pad positions, and these positions can be somewhere from 1 till n. And it says that Alice is stuck at the corner. How is that happening? Because it says that Alice is here at 1 and Bob is here at 2. This is one case. So, and the different cases when Bob is standing at n minus 1 and Alice is standing at n. Look at in both these cases, Alice is already stuck because here Alice cannot move to this position because Bob is already standing. Alice cannot go to the left as well because there are no valid indices. So Alice cannot make a move and it definitely has to lose. So the answer for all these cases is no as well. Great. Now let me discuss the third test case. So this is the third case when suppose A and B A and B are of different parities, are of different parity. What does that mean? That basically means that A is even and B is odd, or vice versa. So A is even, B is odd, or say A is odd and B is even. So what do you think should be the answer to these cases? Anyone in the chat? Okay. So let me discuss this, that if A is even and B is odd, what will basically happen is Alice can never win the game. Why so? Because first of all, you have to understand this very beautiful invariant in the problem. So this is something which is an invariant. What is an invariant? The invariant is something like this, that if Alice, so if Alice is at an odd position, is at an odd position now, then basically it will move, it will move to an even position in the next step. It will move to an even position. Why so? Because I hope this is clear, right? Because if suppose Alice is standing at some position I and I is odd, so for example, I is 5. So in that case, Alice can move either to the left or to the right. In both these cases, it will move to an index which is I minus 1, which is 4, or I plus 1, which is 6. And both of these are even integers, right? Basically, an odd integer is always surrounded by even integers. So that means if Alice is at an odd position, it will move to an even position. And if it is an even position, it will move to odd position in the next step. So basically, what happens is, suppose Alice starts at an even position and Bob starts at an odd position. Then at the first step, Alice makes a move and goes to an odd position, right? Then Bob makes a move and goes to an even position. And this thing continues. This thing continues. Note that after every step, Alice and Bob has to land up at different cells. One has to land at an odd cell and the other has to land at an even cell. Like after every step, both of them cannot land at the same step. So basically, if you understand, then Alice can never force Bob to win a game here. Let me show this using an example. So suppose this is the case. These are the lily pads. Let me draw the indices. So let me write them down. So this is 1, 2, 3, 4, 5, 6, 7, and 8. Let me say, suppose Alice is standing at some position A, which is at 2, and B is standing at some position 5. So Alice is initially standing at an odd even position and Bob is standing at an odd position. So what should happen? In the next step, Alice will definitely move to some position which is some position which is odd, right? So after the next step, Alice moves here. Then Bob moves to some position which is even. Either it goes here or it goes here. So Bob moves to some position which is even. Then now Alice has to move back to an even position, right? So now Alice cannot jump here. So suppose Bob has came here, then Alice cannot jump here because that would lead to an overlap. So Alice has to go back basically. So that basically means that Alice cannot force Bob to win the game, because in order to force a win, what should be the case? If you have to force a win, then basically suppose this is the array and these are the last two sets. If Alice needs to force Bob for a win, then Alice has to somehow reach here, Bob has to somehow reach here, then Bob should try to go here, but Bob cannot go here and then Bob will lose. This is what the ideal setup should be if Alice wants to force Bob to win the game, right? But this can never happen. Why? Because, because at this step, Alice has moved here, and at the same step, Bob is also trying to move here. But because of this invariance, that after the same number of steps, Alice and Bob should be in cells of different parities, they cannot be in the same cell. So such a condition can never exist, that Alice and Bob, after the same number of operations, try to move at the same cell. So that is the reason if Alice and Bob, A and B, are of different parities, then Alice can never force Bob to win the game. Is this case clear? Guys, please confirm once. Okay, Nikunj says that why not the difference between them less than one work? Nikunj, can you explain your doubt a bit? Okay, so Anand asks who wins here. So here what basically happens is, see, what does the question asks for? The question does not ask for who wins here. So I do not care about who wins. The question simply asks that can Alice always forcefully win? So the point is that I know that in this case, Alice can never force Bob to be in some corner. So since Alice cannot force Bob to win some corner, I'm sure that Alice cannot force a win. It may happen that Bob wins. It may also happen that it remains a tie and none of them can force the other to lose and the game continues forever. But whatever happens, I do not care. Because the question just asks that can Alice force a win, which it cannot. Correct. So in order to Alice to win, basically both A and B have to be of the same parity. So let me show you using an example. So look here. Suppose I have these indices. So Alice is, suppose these are the indices. Suppose Alice is here at 2 and Bob is here at 4. And now suppose the game continues. What would Alice do? It is always favorable for Alice to move towards Bob in order to make him lose. So in the first step, Alice moves here. So if Alice moves here, Alice basically comes here and Bob remains here. This is after the first step. So in this step, Alice has moved. Now it's Bob's turn. So it's Bob's turn. What Bob needs to do? Now Bob cannot go here because Alice is already there. So Bob cannot land at a cell where Alice is already standing. So Alice has basically forced Bob to go backwards. So basically, Alice has to stand here and Bob has to go backward. After this, Alice can actually follow the same strategy. So after this, Alice can force Bob that, okay, I will again move towards you. So Alice can force Bob that, okay, I will again move towards you. So Alice will come here and Bob stays here. Now Bob is again forced. Bob has no help but to move at the last cell because Bob cannot come here, right? So Alice again stays here. Bob moves here. This was Bob's move. And finally, what does Alice does? Finally, what does Alice does? Alice again moves towards Bob. And look, when Alice moves towards Bob, so this is the configuration that A is here, Alice is here, Bob is here, and now Bob has already lost. Because now Bob cannot go here because Alice is already standing here. Bob even cannot go towards the right because there are no invalid positions. So if Alice and Bob are at the same parity A and B, either they are both at even positions or they are at both the odd positions, you can actually play on pen and paper and observe that Alice can force Bob to lose the game by just always moving towards Bob in the same direction. But note that when when A and B, these values are of different parities, this case will never happen. Like Alice will never be able to enclose Bob within some condition. Why will this not happen? Because what will happen is, because of that invariant, so suppose in this case only, suppose this is not where Alice is and suppose this is where Alice is. So let me explain this. So, so suppose here is where Alice is. Now what happens is, okay, so let me write them again. So Alice can again use the same strategy that, okay, I will move towards Bob. Great enough. So Alice moved towards Bob. So A is here and B stands here. Now it's Bob's turn. what will Bob do? Bob can actually move towards Alice. So Bob can actually move towards Alice to force Alice to go backward. So if Bob actually moves towards Alice in this step, so in the next step, what does Alice can do? Alice cannot go forward because Bob is already standing. So Alice actually goes backward. So Alice has to actually go backward to the position A. So because of some invariance that Alice and Bob maintain their parities and they flip their parity every time, actually when A and B are of different parities, they can never enforce. Alice can never enforce Bob to win the game. Okay. Okay, Nikunj, you said that okay, if the absolute difference is greater than one, then you can always force a win. That is not the case. Like I probably showed you this example where Alice and Bob are very far apart. So Alice and Bob are very far apart, but still Alice cannot force Bob to win the game. So writing just calculating the distance was not enough. So is this clear? Can everyone confirm? Okay, great. So let me discuss the code once. So here is the code I have written. It is as simple as that we take n, a and b as input, and then we see that, okay, if n is 2, then we have already discussed this case that we will print a no. If a and b are of different parities, then also we will print a no, because we know that it is never possible for Alice to force Bob to win the game. If A is 1 and B is 2, we print a no, because that means Alice is enclosed at some corner of the grid and it can never win. Same happens when if A is n and B is n minus 1. And in all other cases, so basically the case which is remaining is when Alice and Bob both stand at cells of the same parity. In that case, Alice can force Bob to win the game by actually moving towards Bob every time. So in that case, we actually print a yes. Okay. So any idea? Or any doubts on this? Yes, Anand, your code probably work. No, just a second. Anand, I think you did something very similar to me, apart from writing the corner cases. So I hope an idea is very similar to that should work, because checking whether absolute value of a minus b is a multiple of 2 or not basically means that you are checking a and b are of same or different parities. Okay. So I hope it's clear. So let's start with and discuss the problem number B. So here is the problem. The problem says that there are n different types of magical materials numbered from 1 to n. Initially, you have AI units of material I for each I from 1 to n, and you are allowed to perform the following operation. It says that select a material I, where I can be from 1 to n, then spend 1 unit of every other material j to gain 1 unit of material I. More formally, after selecting material I, update array A as AI equals AI plus 1 and AJ equals AJ minus 1 for all j where j is not equal to I. Okay. So note that all AJ must remain non-negative. That is, you cannot spend resources you do not have. Great. Now what does it says? That it says that you are trying to craft. It says that you are trying to craft an artifact using these materials. To successfully craft the artifact, you must have at least BI units of material I for each I from 1 to n, and determine if it is possible to craft the artifact by performing the operation any number of times, including 0. Great. So let me discuss the problem. The question says that the objective is clear. Here is the input. What does the input to the problem is? The input to the problem is two arrays A and B. So you are given one array A1, A2 till AN, and you are given one more array B1, B2 .bn. And then you have been given the power to do some magical operations. I will explain what those operations are. But using these operations, the final objective is that you need to make the values of ai greater than equal to bi for all I. So you need to make ai greater than equal to bi for all I. If you can do this by applying these operations, if you can do this, you print a yes, else you print a no. Okay, great. So now what remains in understanding the problem statement is that what are the operations? So let me discuss that. What is the operation? The operation is simple. It says that you are given an array a1 to an. You pick some index I, so you pick some index I, increase its value by 1, so make ai as ai plus 1, and for all other values decrease them by 1. So you replace a1 with a1 minus 1, a2 with a2 minus 1, and it goes still, and replace all values by an with an minus 1. For example, so just an example here is that, for example, suppose you have an array which is 2, 3, 5, 7, and 4. Then what can you do? You can pick any one index. So pick any one index. Suppose I pick this 7. Increase its value by 1 and decrease all other values by 1. So by doing this operation, the new array you get is 1, 2, 4, 8, 3. So this, I think the operation is clear. This is what the operation is, and the objective is that you can make any number of operations you want on this A array, and then finally what do you need to ensure? That all the values of ai are greater than equal to bi or not. If you can find a sequence of operations which achieves this for all I, then you need to print a yes, else you need to print a no. So is the problem statement clear? Okay, okay, when you say that basically you need to make the value of ai greater than equal to bi, that means you want that for all indices I. So basically for all indices I, the value at the A array should be greater than the B array. For example, just an example, suppose you have A as 7, 4, 2, and 9. And suppose you have B as 6, 3, 2, and 4. Then this is where the condition AI greater than equal to BI, AI greater than equal to BI for all I is satisfied. What do I mean by that this condition is satisfied? This means that look at every index. Look at every index and compare these two values. The value at the A array should be greater than the value at the B array. So 7 is greater than 6. 7 is greater than equals to 6. 4 is greater than equals to 3. 2 is greater than equals to 2. And 9 is greater than equals to 4. Since it satisfies for all indices, I say that, okay, this condition is satisfied. I may have one more test case. So for example, if I have A as 5, 2, and 4, and I have B as 1, 8, and 2, then look here that you find a test case, then you find an index where the value of AI 2 greater than equal to 8 is not satisfied. So what do you say? You say that, okay, this condition, AI greater than equal to BI is not satisfied. So I hope what is the condition that is clear. Yes, Ishant, we are discussing the second problem. Okay, great. So I think the problem is clear. Now let us discuss what can be the solution. So I have been given an array A. So let us start with an example. So suppose I have been given some array A, which is 2, 5, 4, 1, and 8. And this is my A array. And suppose this is my B array. And suppose this is 1, 8, 2, 4, and a 5. Great. Now, what do I need to ensure? I need to ensure that all values in the A array is greater than equal to B array. That means I need to ensure that this value 2 must be greater than equal to 1, which is already there, so that it's not an issue. But look at these indices. These are the problematic indices. And even this is a problematic index, because here the value of AI is less than the value of BI. Here also the value of ai, which is 1, is less than the value of bi, which is 4. So we need to somehow apply operations on this A array so that every value, at every index, the value at A becomes greater than equal to the value of B. So before making any comment, I have a claim. So first of all, I will tell you what my claim is, and then we will try to understand why it is correct. So what is my claim? My claim is that you cannot increase you cannot increase two indices two two indices of A at the same time. You cannot increase two indices of A at the same time. So this is what my claim is. What do I mean? I basically mean that look here. Here I need to increase the value of 5. I need to increase the value of 5 and I have to make it more than equal to greater than equal to 8, right? Otherwise the condition will not be satisfied. Similarly, I have to increase the value of 1 here and I have to make it at least 4 in order to satisfy the conditions. Now my claim is that whenever there are more than 2, there are greater than equal to 2 indices where you need to increase the value of A, then you can never solve it and the answer is no. So anyone, everyone clearly understood what the claim is? We have not yet proved the claim. Okay, great.
Yeah, like we need to increase every element by one wrong side, na?
Yes, in one operation, I have to increase some index by 1, and while doing it, I have to decrease all other elements by 1 as well.
Right, right.
Right. So my claim is that you cannot increase at least two indices of A at the same time. So why is it true? Let me show this. So suppose I have this array A. So I have 3, 4, 7, 6, and a 2. First of all, before doing anything formal, you can actually play on pen and paper to see what happens. Suppose I need to increase this value of 4 and I need to increase this value of 6 at the same time. So suppose I somehow want to do operations so that I need to increase the value of 4 by 1 and I need to also increase the value of 6 by 1. Suppose this is what my objective is. Look that I can never do this. Why? Because when I need to increase this value of 4, it always makes sense to make the operation at 4. If I make the operation at 4, what happens is the new array I get is the value of 4 increases by 5, but the values of all other indices decrease by a 1. So this is the new array I get. But note that while increasing this value has actually decreased. Now if I try to increase this value, suppose I have seen, okay, that 5 has got decreased. So let me increase the value of 5 to 6 now. If I try to do that, and if I try to increase this value, so this becomes 6, but then all other indices get reduced by 1 again. So it becomes 1, it becomes 4, it becomes 5, it becomes a 0. So look at that there are two competing factors playing against each other. If you increase the value of 4 by x, that means the value of 6 decreases by x at the same time. Similarly, if you increase the value of 6 by x, then the value of 4 decreases by x at the same time. The operations are made in such a way that whenever you need to increase some value, it has to be on the compromise of some other value. So that means two values cannot be simultaneously increased at the same time. Is everyone convinced with the argument? Great. Yes, it will never be balanced because increasing one index actually decreases the values of the other index. So whichever index you pick, the value of other index actually decreases and you cannot increase two indices at the same time. So I hope that is clear. Let's look a few test cases which are given here. So look here. Uh, this is a test case which we can see. Here we have a 1 and a 2. Whenever I have a 1 and a 2, okay, so let me copy this. So this is what the test case is. Let us discuss this. So the test case says that we have a 1, 1, 3, and then we have a 2, 2, 1. And then we have a 2, 2, 1. So this is the test case which we need to discuss. So look that here there are two indices where the value needs to be increased. Here AI is less than BI. So we need to increase the value at this index. Also, here also AI is less than BI. So we need to also increase the value at this index. But we have already seen that these operations are such that this is never possible. So that means the simple answer for this test case is no. The simple answer for this test case is no. Whenever you find at least two indices where you need to increase the value of AI at the same time, just output no. There is no cross questioning. So for example, suppose you have this test case where you have a 7, you have an 8, you have a 2, and then you have a 12. And suppose this is 3, this is 9, this is 6, and this is a 15. So look at count how many indices are there where you need to actually increase the value of AI. So here there index where you need to increase the value of 8, you have to make it at least 9 for the condition to be satisfied. Same goes at this index and same goes at this index. So since there are greater than equal to two indices where the value needs to be increased, the answer for this is no. Great enough. Anyone with any doubts on this? Okay, great. So I hope it's clear. So let me count this in a variable. So what do I count? Let CNT be number of indices I where AI is less than BI. If AI is less than BI, that means I need to increase the value of AI there, and I know that I cannot increase the value of AI at two indices. So that means after making this count variable, there are three cases. The first case is if CNT is greater than equal to 2. If CNT is greater than equal to 2, it's simple. The answer is no. We have already discussed this. The second simple case is what if CNT is equal to 0? Can anyone tell me the answer? What if this value of the CNT variable is actual 0? Great. If the value of CNT is 0, then the answer has to be yes, right? Because if the value of CNT is 0, that means the condition AI greater than equal to BI is already satisfied for all indices I. So we need to make no operations. So no operations are required and we can actually solve it. Great. So the second test case is clear. The second case is clear. The third and the final case which remains is like we have already handled all values of CNT greater than equal to 2. We have handled the value where CNT is equal to 0. The final case which remains is what if CNT is equal to 1? So let us discuss this case where CNT equal to 1. What do I mean by CNT equal to 1? Basically in the array, so suppose this is my A array 7, 4, 1 and 8. And my B array is something like this 6, a 2, a 9, and a 4. So there is only one and exactly one index where the value of AI needs to be increased. Look that at all other indices, the value of AI is already greater than equal to BI. So we are not forced to increase the value of AI at other indices. So what can you actually do? Any idea? Great.
We
We
can
have to
check
actually
whether
yeah, sure. We can actually check. Like I know that I have to make this value 9. So what I can do is I know that I have to increase this value by 8. If I increase this value of 8, all other values will actually gets decreased by 8. So these values will get decremented by 8. And what array will I get? I will get a -1. I will get a -4. I will get a 9. I will get a 0. And then I can simply check that, okay, is the condition AI greater than equal to BI satisfied for all indices or not? Here, it is clear that we have a 6, 2, 9, and a 4. Here, here the condition is not satisfied. Sorry, here we will get a no because there are indices where the value of AI actually becomes less than AI. So after you find out that, okay, the value of my count variable is 1, That means there is exactly one index where you need to increase the value, and the value will get decreased at all other indices. So why not decrease it actually and then check, okay, whether is AI greater than equal to BI or not? So I hope that is clear. I implemented the same logic. What you can do is, so let me take this example only, 74186294. So I have 74186294. What I did is I made two variables. I made two variables. So I made one variable mn. So mn stores what is the value I need to increase. So basically mn stores 8 because I need to increase 8 to 1 to get this value of 9. And mx stores what is the maximum value I can afford to decrease. So look that I can decrease this value by 1 only. Like if I decrease 7 by more than 1, then I will get an issue here because the value will become less than 6 and the condition will not be satisfied. So I can decrease this by 1 at most. I can decrease this by 2 at most. And I can decrease this index by 4 at most. So what is the maximum allowed number of operations I can make? I can make the minimum of all them, which is 1. So I cannot make more than one operation. If I make more than one, so this condition says me that, okay, you have to make at least 8 operations to match at this index. In order to match this index, I have to make at least 8 operations. And this says that you cannot make more than one operation, because if you make more than one operation, there will be some index in the array where the value of AI will drop BI. So now I will just check that, okay, this value of mx should be greater than equal to mn, right? Because the number of allowed operations should be greater than equal to the number of operations which I need to actually make. There are actually multiple ways to implement this. You can actually, I think the simpler idea would be to just create the new array and then check whether the condition is satisfied with this or not. I have implemented this, but all type of implementations are fine. And I would recommend you to understand the logic and write your own code. But let me explain you the code a bit. So here, this is what I have done. So I've taken n as input. I've taken the two vectors a and b as input. I've made this count variable. So whenever I see that, okay, the value of ai is less than bi, I have increased the value of count. Then as we discussed, if the value of count is greater than equal to 2, we can never increase both the indices. So it has to be no. If the value of count is 0, that means the condition is already satisfied. We can simply print a yes. For all other cases, what do I do? Whenever I see that, okay, AI is greater than equal to BI, I take a minimum with MN. So that basically stores what is the maximum number of operations allowed. And MX is basically BI minus AI. So that is basically the number of operations I need to actually do. And the number of operations I need to actually do should be less than equal to the number of operations which are allowed. If that happens, we print a yes, and otherwise we print a no. I think, just a second. Yeah, okay. So while explanation, I missed these two variables. So this should be an M. Okay, just a second. So this should be mx as per the code. So if mx is greater than mn, then we print a no. So this is mx and this is mn. But these variables have their meaning, and I hope you understand that. Probably it will be better if you try to write your own code, and I hope that the logic is clear. So guys, please confirm once if it's clear, and please ask if you have any doubts on this problem. Otherwise, we will move to the next one. Okay. So since I do not see any more doubts in the chat, let us move to problem C. So this is problem C. It says the trail. So the question says that in the wilderness lies a region of mountainous terrain represented as a rectangular grid with n rows and m columns. Each cell in the grid is identified by its position I, j, where I is the row index and j is the column index. The altitude of cell I, j is denoted by aij. However, this region has been tampered with. A path consisting of n plus m minus 1 cells starting from the top left corner 1, 1 and ending at the bottom right corner n, m has been cleared. For every cell I, j along this path, the altitude aij has been set to 0. And this path moves strictly via downward or rightward steps. Okay. Now the question says that to restore the terrain to its original state, it is known that the region possessed a magical property before it was tampered with. All rows and all columns shared the same sum of altitudes. More formally, there exists an integer x such that all row sums and all column sums are x. Your task is to assign new altitudes to the cells on the path such that the above magical property is restored. It can be proven that a solution always exists, and if there are multiple solutions that satisfy the property, any one of them may be provided. Okay. So let me explain what does the problem statement says. I felt that the problem statement is a bit lengthy than what it actually meant, but the problem statement is something very simple. So here what it is. So in the input, you will be given some grid. So you will be given some grid. So this grid will have n rows and m columns. So it has n rows and then it has m columns. Okay. Now there are some values which are written at every cell of the grid. Okay, just a second. Okay. So in the input, basically the question says that there is some path which is given, which is already zeros. So this is some path from 0, 0 to n, m, where everything is already 0. And in rest other paths, there are some values given. So there are some other values given. We need to fill or we need to populate all these values along this path of the grid with some values such that all row sums and all column sums remain the same. So is the idea clear? There is a grid given. In this grid, there exists a path where the values are all 0, and this path is also given. We need to fill values in this path with something, with some values, and then print the final grid so that at the end of the day, all the row sums and the column sums are equal. So is the problem statement clear? Can I have a quick yes or any doubts? Okay, great. So the problem statement is clear. The path would be given to us as a string of downs and rights. So suppose this path can be actually given to us as a down, then a right, then a right, then a down and a down and a right and a right and a down. So basically it would look something like a D, R, R, D, D, R, R and a D. So a string would be given to us and a grid would be given to us. This string would actually represent the path which is filled with all zeros, and we need to fill some values in this path such that the row sums and the column sums will become equal. Okay, good. Okay, good. So now, I have an idea. First of all, what should be the row sum and the column sum be equal to? I do not find any constraint in the problem. So I have an idea that, okay, what we will try. So let me try. So this is something which I will try. I will try to make all row sums and column sums equal to 0. Let us see that can we do this. So we will fill some values in this path. In every cell, we will fill some value such that the sum of the entire rows, all these rows and all the columns actually become 0. So let me see if we can do this. But let us take a solid test case which is given for a clear understanding. Okay, just a second. Okay. So let me take this test case. It says 0, 2, 3, 0, 0, 0, 3, 1, 0. So we have this grid 0, 2, 3, and then we have a 0, 0, 0 and a 3, 1, 0. And then we have a 0, 0, 0, and then we have a 3, 1, 0. Great. And what path we are given? We are given the path DRRD. So this is the path which we are given. The path is DRRD. So it basically represents this path, a down, then a right, then again a right, and then again a down. For a quick sanity check, you can see that it starts from 0, 0. So it has started at 0, 0. It ends at n minus 1, n minus 1. It comprises of only down and right paths. And most importantly, all the values in the grid at these paths are actually all zeros. Okay, great. So I need to fill values in the grid so that the sum becomes all zero. Let me write it once again. So I have a 0, 2, 3, 0, 0, 0, 3, 1, 0. Since these zeros need to be overwritten with something of our choice, I keep them blank. So let me fill them with blank spaces. These are values which I need to write so that all the row sums and all the column sums become zero. So let me see what happens. So what value do you think I can write here? So what value can I write here to make all the row sums and the column sums zero? -5. Yes, great. So the only choice which I have to fill here is -5. There is no other value which I can fill. Because if I fill some other value, the sum of this row would not be basically 0. Because in order to make the sum of these two values is 5, I have to place a -5 here so that the entire sum becomes 0. Great. So now I move to this step. So what value do you think can I put at this place? Okay, so people are saying 2, and yes, you are right. So I basically need to fill in 2 here. Because if I do not fill a 2 here, then the sum of this column will not become 0. That is clear, right? The best part of this problem is that using this, at every cell, you can uniquely identify what value you need to put here. So can someone quickly tell me what these three values should be? Okay, so -3, 1 and -4, that's what Anurag says. Let's have a quick look. So -3, why should it be -3? It should be -3 because when we come here, what do we see? We see that okay, the column of this sum, the sum of this column should be 0, right? So we have already a 2 and a 1, so I have 3 sum already there. So I need to fill a -3 to neutralize it. Now come here. So you already get a 2 and you have got a -3. So the sum is already -1. So I need to actually fill a 1 here to make this row sum 0. Now, now come here. What do we see? We see that a 3 and a 1. So I need to actually fill -4 here so that the sum of this row is 0. What is interesting is that when we try to dry run it on pen and paper, finding all these values are very simple. All these values are something which comes very clearly if we remember what are all the row sums and what are the column sums. So let me look at very smartly what I have done. Okay, so let me try to 0, 2, 3, 0, 0, 0, 3, 1, 0. So this is the test case which we had 0, 2, 3, 0, 0, 0, 3, 1, 0. Great enough. And we have already seen that it is not very difficult to identify what values do we need to put at every step. Basically, what we do, we try to iterate over the string DRRD. So the first character is D. So I need to go down. Remember that whenever I need to go down, I can actually look at the column sum and try to understand what value do I need to put here. So I look that, okay, the column sum is 5. So the column sum is 5. So what value do I need to put here? I need to put a -5 here. Great. So now now I have reached this position. Now I need to move a right. When I will move a right, Okay, sorry. I was saying this is a row sum. Sorry for the mistake. This sum which we were looking was actually the row sum and not the column sum. I drawn it right, but I told it wrong. When we are going to down, we can actually look at the row sum and find out, okay, what value do I need to look at it. Now when I'm going right, I need to check this column sum and try to understand what value do I need to fill at minus 0 here. So when I go to the right, I see that, okay, I have a minus 5 and a 3. I look at the column sum. The column sum is 2. So that means I need to fill a minus 2 here in order to get my value. Great enough. Let me rub these zeros. So now after this, I've reached this part. So when I reach this part, okay, yeah, Ishant, did you raise your hand? Any doubts?
Yeah, I was asking that here we have only three rows and three columns. But what if there are five rows? So we don't know na, that what is below -2, like below the star. Like how do we decide that we have to put -2 here?
Okay, so the idea is that even if you have a lot of rows, like let me take a larger example. Uh,
Yeah,
so I will so let me take a larger example. So suppose this is an example with 5 rows, and for example, let me take 4 columns here. And suppose we are given some path, right? So we are given some path from 0, comma 0 to this n minus 1, m minus 1, right?
right.
So suppose this is the path which I am given.
Hmm.
So my idea is that whenever you see a down, whenever you see a down, you basically look at the column sum. And right, whenever you have a right, you basically look at the row sum. This was what I was explaining. And the
Yeah,
beauty of paths which involve only down and right steps is basically this, that when you find a down, when you actually go to down, so basically you will never touch this row ever. Okay, I again made a mistake. Just a second. So this should be a row sum and this should be columns. So this should be row sum and this should be column sum.
like
So,
suppose we have a row sum of five, right? And we have
okay.
two or three empty positions over there. Then to counter five, we will put -5 at the current index, right?
Okay, yeah, that was what I'm explaining. That if you go down here, then in this path, it is never possible to have more empty positions on this row, right? So whenever you have a down here, you will actually look at the row sum. And in this row, you can never have more than one empty position. So you already know the sum of these values. You can actually fill,
Okay.
so suppose the sum of these values is S, you can actually fill a minus S here. And it will never create a problem because since you are going down once, you will never touch this row.
Right,
So again, let me come to the second row. You're again going down here. That means you will never touch the second row ever. So try to find the sum of these values. If that is S, then you just fill a minus S here.
right,
Now here you are going right. When you are going right, then look at the column sum. This is the beauty of it. Whenever you are going right, you are basically leaving this column. So there are no more empty positions possible in this column. So find the sum of all these values, and then just if the sum of all these values is say S, then fill a minus S here. So is the idea clear?
yeah, clear.
Yeah, this would probably work with grids of any dimensions. And basically, what do you need to do is you need to somehow store the values of the row sums and the column sums efficiently, and then you have to update them correctly. Even if you update them correctly, the values at all the empty cells can be actually found out. Let me show you all the code, and then if there is some issue, then we can actually have a dry run on a test case. So this is the code. I take n and m as input. After taking n and m as input, I basically make a vector of size nm, which I call a. I take the string as input, and then I take the entire grid a as input. Great. Now I have I have made two vectors r of size n and c of size m. So Ri basically stores the sum of the ith row and Ci stores the sum of the ith column. So look what I have done. I have iterated over all rows and initialized the sum variable, found the sum for all cells of that particular row and stored it in Ri. Similarly for Cj, I iterated over all columns here, found out the sum of all the cells of the jth column and stored that value in Cj. So basically, Ri and Ci stores the sum of the ith row and the ith column respectively. Now look at this part of the code. I start with x equals 0 and y equals 0. So when I start with x equal to 0 and y equal to 0, that basically means that I am at the origin, right? I am at 0, comma 0. And this count is nothing but the pointer. So we are iterating over the string, right? And the string is of length n plus m minus 1. So we are iterating over the string. So now there are two things we can get. We can get a down or we can get a right. So what did we discuss? We discussed that whenever we will get a down, so whenever we will get a down, what we will look into? We will look into the row sum. So look what I have done. Whenever I've got a down, I look at the row sum that is stored in Rx, and then I say that okay, the value in the grid should be negative of that, right? Because the sum of the remaining, if the sum of the remaining row is s, then I need to store minus s there. So I basically store the value of AXY as minus RX. So if I've stored the value of AXY as minus RX, so that means basically in the xth row and the yth column, I have inserted a value AXY. So I update the row sum and the column sum. I add AXY to the row sum and AXY to the column sum as well. And then I increase the value of X. Since I was going down, I need to increase the value of X, right? Same with the right case. When we are doing the right case, we actually look at the column sum. And then this is very similar. We update the row sum and the column sum and increase the value of y. Then we increase the pointer, and finally we iterate the string in the same fashion and finally print the grid. So is the idea clear? Anyone with any doubts? Vaibhav, it would be a bit difficult for me to review your code in the meet. You can actually ask the mentors and they will help you with the doubt. Okay, let me show how I'm initializing the R and the C values. So basically, if I have a grid, so this is a very standard idea which will, so suppose I have 1, 2, 3, 4, 6, and 8. Suppose this is my grid of 2 rows and 3 columns. So what do I make? I make R a vector of size 2. So I make R of size 2 and I make C of size 3. Okay. So suppose this is my R array. So this is my R array of size 2. What do? I iterate over both the rows. I first take the first row and then I add up these values. I add up these values. So the value I get is 6 and I store it here. So I basically store 6 here. Then I go to the second row and then I again add up these values. So I add a 4 and a 6 and a 8. So I get an 18 and I store it here. So this is something basic, simple iteration and computing the sum. Nothing very complicated. I do the same with the column grid. So I now basically have 3 positions. So I go iterate the columns one by one. In the first column, I look at the positions 1 and 4, add them up. So I get the value of 5 and store it here. So I store a 5 here. I do the same over this. I add both the indices. I get an 8 here. And finally, I get an 11 here. If you look at my code, this is exactly what I have done. Look here, that when I'm computing Ri, I am basically iterating over all rows, I from 0 to n. I'm maintaining a sum variable. Then I'm iterating over all columns in that row. So on all columns in the ith row, I'm going from j to 0 to m, adding up the values and finally storing it in the row sum, Ri. I did this exact same for the column sum. Okay. Okay, so it's clear, right? If I do not see any more doubts, then we can. Okay, Adarsh wanted to look at the code once again. So let me show this. Let me again explain the code once more in short. So basically we take n and m as input, then we take the string as input, then we take the grid A as input, then we compute the row sums and the column sums here. This is something very simple in order nm traversal. We just iterate over all rows, go to all the columns, find the sum, and then store it in the row sum. Similarly, we iterate over all columns, look at all the rows, compute the sum, and store it in column sum. I hope this part is clear. Now here is the main part of the code. I initially start from origin. That is, I start from 0, 0. So x is 0 and y is 0. CNT is nothing but the pointer of the string. So basically where I'm actually standing at. So since the length of the string is n plus m minus 1, so the while loop runs till the value of CNT is less than n plus m minus 1. Here, now if I look that, okay, the string is D, the CNTth index of the string is D, that means we are going down. And I have told you that whenever we are going down, basically we are leaving that row ever. So since we are leaving that row forever, I can find actually fill the value of AXY with negative of the row sum there. And then finally, I have to update my row and column sums. Since I was going down, I increase the value of X. Same I do for the right case. Whenever I'm going right, that means I am actually isolating or forgetting about that column forever. I am leaving that column forever. So I can use its sum to actually compute the value of AXY. I compute it. I simply again update the value of Rx and Cy. Since I was going right, I do a y plus plus. And I finally go to the next variable of count, basically moving to the next step of the path. Finally, after all this, we just print the grid. Okay. Okay, great. So Kavi asked a very interesting question. He asked me that why should the sum of the all rows and all columns should be actually 0? Basically, 0 is something which I liked and it was completely of my choice. You could keep any other value. So for example, your favorite number is 7. So let me take this test case again. So suppose I have this, I have a 2, 3, and then I have this open. And let me look at what the test case was. So it was okay. And then we have a 3, 1 and an empty space. So we have a 3, 1 and an empty space. So suppose you do not like 0 and suppose your favorite number is 7 and you will try to make all row sums and column sums 7. You can use the exact same idea. So basically, you know that this sum is 5. So store a 2 here. So simply store a 2 here. Now, when you go downwards, you look that okay, there is a 2 and there is a 3 already. So the sum is 5. I need to make it 7. So why not put a 2 again here? Great. Now come at this part. So now you already see that, okay, I have a 2 here, I have a 1 here. So I need to fill it with a 4 in order to make this row sum 7. You again go to the right. So now when you go to the right, you look at this sum. You have a 2 here, you have a 4 here. You have to fill it with a 1, right? So that this row sum becomes 7. Now again you go here. You see a 3, you see a 1, and then finally you store a value of 3 here in order to make this sum 7. So instead of taking 0, you could actually take any constant and write the code. I have taken 0 as it was, and it was completely arbitrary. Any value would have worked fine. Okay. So let us start discussing the next problem. Okay, Pradyuman says that m not equals to n, then the only possibility is sum equals 0. Okay. So let me try with a test case. Actually, I have not thought about this in the contest. I'm not very sure if that is the case, but it may happen. So I have suppose a 2, 3 here, and then I have an empty cell here. And finally, I have a 3, I have a 1, and suppose I have an empty cell here also. And then and suppose I have a 4, and I have a 2 and an empty cell here also. So the value of m and n are not equal here. So let me check that, okay, can we make the sum 7? Okay, so we have got a 5 here, then and then we fill a 2. That's fine. So now I have got a 4, then a 7 and a 9. So I have to fill a -2 here. So we are trying to make all row sums and column sums 7. So now I go from -2 to this step. So I see that, okay, the sum is already 5 here. So that means I need to put a 2 here. Now I go at this position. I see a -2 and then a 2. And so you have to fill it with a 7. Then now I have a 3 and then a 7. So at this part, since I have a 3 and a 1, I need to fill it with a 3. Okay, I got it. Okay, so finally, when I reach this part, then we get two contradictory values because the row sum and the column sum cannot be matched. Okay, that was a good observation. Personally, I did not note this. Probably I was lucky then to try check with the value 0. Okay, probably let's like I'm not very sure why what should be the like why should always, or I do not have a formal proof why should 0 always work and other values should not. Uh, so let's skip it for the moment, and then if I get a formal proof, I would probably write in the chat somewhere. I apologize for it, but I did not think about it. Okay. So let's start with the fourth problem of the contest. Yeah, Hariom, I actually tried a sample where n is not equal to m, and I've seen that using a value other than 0 would have actually caused an issue. So let's start with the fourth problem of the contest. So this was question D, and it says that a crow is sitting at position 0 of the number line. There are n scarecrows positioned at integer coordinates a1 to an along the number line. These scarecrows have been enchanted, allowing them to move left and right at a speed of 1 unit per second. The crow is afraid of scarecrows and wants to stay at least a distance k ahead of the next scarecrow positioned at or before it. To do so, the crow uses its teleportation ability as follows. Let x be the current position of the crow and let y be the largest position of a scarecrow such that y is less than equal to x. If x minus y is less than k, meaning the scarecrow is too close, the crow will instantly teleport to position y plus k. Okay, great. This teleportation happens instantly and continuously. The crow will keep checking for scarecrows positioned at or to the left of him and teleport whenever one gets too close, which could happen at non-integral times. Note that besides this teleportation ability, the crow will not move on its own. Your task is to determine the minimum time required to make the crow teleport to a position greater than or equal to L, assuming the scarecrows move optimally to allow the crow to reach its goal. For convenience, you are asked to output twice the minimum time needed for the crow to reach the target position L. It can be proven that this value will always be an integer. Note that the scarecrows can start, stop, or change direction at any time, possibly at non-integral times. Okay. So let me try explaining the problem statement. So here is the input. So the question says that we are given some integers a1 to an. So we are given some integers a1 to an, and these are the position of the scarecrows. Okay. And these are given in strictly increasing order. Great. Now there is a crow which is standing at 0. there is a crow which is standing at 0. And then there are scarecrows standing at these positions A1 to AN. Okay, great. Now, this crow is actually afraid of the scarecrows. So and these scarecrows can actually also move. So what happens? These scarecrows will move in some fashion. The crow, using basically by some fashion, is afraid of the scarecrow and will try to escape. By trying to escape, we need to find out that there is some index L here, which is given as input, and we have to find out what is the minimum time such that the crow exceeds this L distance. So basically, the scarecrows have to somehow move optimally so that they can make the crow throw away this farm. Basically, it exceeds such that it leaves x equal to L in minimum time as possible. So that is what the question says. Now, how does the crow and the scarecrow move? So it basically says that the crow teleports. So suppose this is the crow. This is the crow and it is at some position X. First of all, if all scarecrows are at the right of the crow. So if all the scarecrows are at the right of the crow, then the crow does not move. So the crow stands here still at X. Okay. Now, in some other case, if you look at some other case where suppose there are some scarecrows to the right of it. So here is the crow and suppose there are some scarecrows to the right of it. Okay. So these are the scarecrows which are right of it. And suppose this scarecrow, the nearest scarecrow is at the coordinate y. Now it says that, okay, if the distance between them is less than k, then if the distance is between them is less than k, then what will the crow do? The crow will actually jump and go to a value which is such that the distance becomes k. So basically the crow will go from x to y plus k. So this is how the crow moves. The crow looks at all scarecrows towards its left, finds the nearest scarecrow. If it sees that the distance is greater than or equal to k, it is fine. If it sees that the distance is less than k, then it moves k distance apart from this at this cell. Okay. So is the question clear? This is how the crows and the scarecrows move. The scarecrows need to move optimally in such a fashion so that the crow reaches x equal to L in the minimum time possible, and we need to output the minimum time. Okay. So I hope the question is clear. Okay, what is x? How are we determining x? So x is the position of the crow at some instant. So basically x is initially at 0. So x is not a part of the input. The crow is initially at 0. The scarecrows move in such a way so that the crow starts moving. So suppose from this from this step, crow goes to some position, say 3. So when it reaches 3, then how does it move? That is basically determined by this rule. So this is basically a rule. What happens? So that it says that if crow is at position X and these are the position of the scarecrows, then this is how the crow will move. So this is a policy by which the crow actually undergoes teleportation. This is not an input or something. Ishant, is that clear? Okay, great. So basically, we need to find an optimal strategy for the scarecrows to move so that the crow reaches x equal to L in the minimum time possible. Okay. So now, what is the idea? The idea is, so initially the crow is at 0. So this is the crow and it is initially at 0. That is fine. And now here there are scarecrows. So here the scarecrow is at some value A1, and then here is some other scarecrow at some value A2, and so on. There are multiple scarecrows. Now, what did I say? That this scarecrows needs to move in such a way that it reaches, so suppose this is x equals L. The scarecrows needs to move in such a way that the crow escapes all this and reaches x equal to L, right? So now what happens? So that means some scarecrow must actually move to 0, because if the crow stands here and no scarecrow actually reaches 0, then there will be nothing at the back. And as per the policy of the crow, if there is nothing at the back, the crow stands still, right? So the crow will forever stand at 0. So there should be some scarecrow which should run and reach at 0, so that the crow actually jumps and starts teleportation. So what do you think? Which scarecrow should go to 0 first in order to ensure that the time is minimized and the crow starts moving? Okay. Yeah, sure, Abhijit. I will take the test case 2 as example. Uh, but my idea is that in order to start the game, the scarecrow, that the first scarecrow has to actually reach 0. Whenever the first scarecrow reaches 0, the crow will basically jump and start teleportation. So for a concrete example, let's start as Abhijit suggested with the test case 2 for sure. Okay, so here it is. It takes 2, 5 and 5 and the value of k is 2. Great. So it says that initially the crow is at 0. So initially the crow is at 0. And then there are 3 scarecrows, one at 2 and 2 of them at 5. So there are 2 scarecrows at 5. So there is one scarecrow here, and then there are 2 scarecrows here. And the value of L is also 5. So we need to somehow do something so that the crow goes here and moves to L equal to 5, and we need to find the minimum time. So what should happen? First, this scarecrow should actually go to 0, right? This scarecrow should go to 0, so that whenever it reaches 0, the crow actually teleports from it. So what happens? So let me draw this. So initially there was 1 at 2 and 2 at 5. So these stars represent my scarecrows. And the crow stands here at 0. What should be something optimal? The optimal is it takes 2 seconds for this scarecrow to reach 0. So what will happen? So it takes 2 seconds. So now this scarecrow has reached here 0. And just as soon as it reaches 0, the crow basically teleports a distance k from here, right? So and the value of k is 2. So that the crow reaches 2 here. Great. Now I will explain why does the scarecrows behave like this. But let me tell you that this scarecrow would actually reach in this 2-second time, when the first scarecrow has actually moved a distance of 2 in this direction, this scarecrow would also move. This scarecrow would also move at 3. So there were 2 scarecrows, both of them standing at 5. They would also move. So suppose one moves at 3, and the other moves at 4, for example. Okay, just a second. Let's forget about the other one for now. So this is my L equals 5. So suppose the other scarecrow moves at 3. In this 2 seconds time, this scarecrow has also moved 2 distance here, and this scarecrow has also moved 2 distance here. Just as soon as the first scarecrow reached 0, this crow teleported and reached k equal to 2. Great. Now what will happen next? What will happen next is basically this scarecrow will start moving. And as soon as this scarecrow starts moving, this crow, since it always needs to maintain a distance k from this, it will also start moving. Similarly, at the same time, this scarecrow would also move in this direction. And both of these things will happen simultaneously. So basically, in half a second, what happens in half a second? So basically, in half a second, this scarecrow has moved to 0.5. So I have this scarecrow at 0.5. This crow, since it always wants to maintain a distance 2 from the other scarecrow, it reaches 2.5 here. And this scarecrow also has moved left and reached 2.5. As soon as it reaches 2.5, the crow sees one more scarecrow at the same coordinate. It again jumps a distance of k. So it again jumps a distance of k and it reaches 2.5 plus 2, which is 4.5. Note that the third scarecrow had actually got enough time before this rush was happening. So the third scarecrow can also move half here, and it could actually stand at 4.5 and wait for the crow to jump here. So the third scarecrow for this entire time actually waits at 4.5. So whenever the crow comes at 4.5, it immediately sees that, okay, there is a scarecrow here, and it will again jump k equal to 2 and reach 6.5. Okay, so what is the time it required to exceed 5? The first 2 seconds where the scarecrow actually moved to reach the origin, and then this half distance here. So the answer is basically 2.5 seconds. We need to double the answer and print as output. That is what is asked.
Can you explain it again?
Okay, sure. Let me explain this. Okay, let us not think about what is happening, but then I will show that how this 2.5 comes. Basically, what happens is,
Yeah, like
initial.
how we are deciding that how much the scarecrow will move, like whether it will move two steps ahead or one step ahead. How we are deciding that?
Okay, that is something I will explain, that what should be the optimal logic of the scarecrows in order to ensure that the crow reaches x equal to L in the minimum time. But here I'm just trying to show that what is the psychology of the scarecrows. So basically, the what happens is that uh, what happens is that there is a scarecrow at 2, and then there are two scarecrows at 5. So there is a scarecrow here at 2, and then there are two scarecrows here at 5. And the value of k is 2. The value of k is 2, right? So that means these two other scarecrows know that that it will take 2 seconds for this scarecrow to reach here. And when this scarecrow will reach here, the value of this crow will jump from 0 to 2 because the value of k is 2. So it always makes sense that these scarecrows in this meantime start rushing towards here. So as they rush towards here, basically what happens is they could actually force the crow to actually move x equal to 5 in the minimum time possible. So basically, this crow 5, what does this crow 5 knows? This crow 5 knows that, okay, that when this scarecrow will reach 0, as soon as it reaches 0, the crow will jump and go to reach equal to 2, and it will try to go equal to 2. So this scarecrow will try to stand at 2 itself, because it knows that if I stand at 2 itself, so the crow will jump and come to 2, it will immediately see me, it will again make a jump. So it is best that if this scarecrow can come from 5 to 2, right? But what happens actually is that you have only 2 seconds to do that. What actually happens is that initially you were at t equal to 2, you had just 2 seconds to reach t equal to 0.
So k
Now,
equal to 2. That's why it is 2 seconds to like go from 2 to 0.
correct.
Right?
No, it's not because k equals 2. It is because the value of a1 is 2. The initial scarecrow stands at 2. It may happen that the value of a1 was 4. In that case, it would have taken 4 seconds for the
Okay.
first scarecrow to
Okay.
reach from 4 to 0, and then the crow would have jumped to k equal to 2 only because the value of k is 2. But what I'm explaining is that, okay, the job of the first scarecrow is simple. It has to go to x equal to 0 and simulate the movement. But look at what is the psychology of the other scarecrows. The other scarecrow would always try to reach a position where the crow actually jumps. So it knows that, okay, that when the first scarecrow reaches 0, the crow will jump to k. So it is best that if the scarecrow stands at k, because if it stands at k, whenever the crow will jump to k, the crow will see, okay, there is one more scarecrow here, so I need to jump again. So that is the way it can compute it can actually travel the most distance in the minimum time. So basically what happens is, here is the crow at 0, and then here there are scarecrows at 2, and a scarecrow at 5 here, and then again a scarecrow at 5 here.
Right.
So now first this crow goes to 0. So what happens is, in this time being, this scarecrow, so let me call this SC1, and there are two scarecrows standing here, SC2 and SC3.
Yeah.
And let me call this the crow.
Right.
So this at t equal to 2, at t equal to 2, this scarecrow SC1 reaches 0.
Right.
And this
And 2
crow,
is SC1.
actually reaches at t equals 2 because it jumps, right?
Yeah.
The scarecrow 2 actually wanted to stand at 2. Like if scarecrow 2 would have the power for infinite speed, maybe it would have stand for 2. It would have standed at 2 because that would help the crow to immediately jump the maximum distance. But scarecrow 2 had unfortunately not got enough time. It had 2 seconds to reach from SC1 to the crow. So basically SC2, the maximum distance it can reach is 3 in the
Okay.
meantime.
Yeah.
Let
Because.
us forget what SC3 is doing. We will think about it later.
Mhm.
Now what happens is, SC1 sees that okay, that the crow is at 2, and
Yeah.
SC2 sees that the crow is at 2. So now this SC2 needs to move here, and have to reach this, so that basically what happens, the crow again jumps, right?
Okay. So basically, the scarecrows are supporting the crow to move
Exactly. The
easily.
scarecrows have to move in the most optimal fashion so that the crow reaches x equals L in the minimum time.
Okay.
This is in analogy something to like that you think that okay, 0 to L is some field. 0 to L is some field, and the basic job of scarecrows is to throw crows out of the field, right? So the
Right.
scarecrows would move in such a fashion so that the crow reaches out of the field in the minimum time.
Okay.
So basically, this scarecrow will try to move in the right direction, will try
Yeah.
to move in the left direction so that it
Yeah.
can throw this crow out.
Right.
But this scarecrow sees that okay, let me also move in the right direction. Because as I move some distance d in the right direction, this crow too is forced to move distance d here. Because the distance between them has to be always greater than equal to k, right? That is what the crow always wants.
Yeah. Right.
So basically what happens is, this scarecrow 2 starts rushing towards left, this scarecrow
Mhm.
1 starts rushing towards right. When after half a second, the scarecrow reaches SC1 reaches 0.5. So it has so D is 0.5, it has moved half the distance. So now the crow reaches 2.5. So the crow reaches 2.5 here. The scarecrow 2 had also got half seconds to reach at 2.5. So the scarecrow 2 also reaches 2.5. As soon as they reach, the crow jumps to 4.5 here.
Okay. Yeah.
Okay, great. Now look at the third scarecrow. It had got 2.5 seconds. The initial 2 seconds when the first scarecrow reached to 0, and then the again half second when this entire thing happened. So it had 2.5 seconds to move to the optimal distance, right? And
Yeah.
suppose the scarecrow 3 had somehow foreseen that okay, the crow will come and reach this position 4.5. So isn't it not the best for the scarecrow to stand at 4.5 itself?
Yeah. Right.
If it stands at 4.5, then whenever the crow reaches there, the crow will immediately jump to 4.5 plus 2 at 6.5 because it has to maintain that distance of k.
Yeah. Right. Like even if the scarecrow three stands at five, then also it will move, na? Because again the distance is less than two.
No, the problem is if the scarecrow if the scarecrow stands at 5, remember
Mhm.
what was our operation? The operation was that the crow looks at what are the scarecrows behind. The crow never looks at what are the scarecrows
Okay.
before me.
Okay. Right.
So it is always so in order to for a scarecrow to become effective, it has to be always at a position less than equal to 4.5 if you want to make it jump. So that is the reason the third scarecrow would actually stand at 4.5.
Okay.
So basically, think something like Think it like this. Think every
Like I did not get the last point. Like you told that the scarecrow must be after the crow, right? Like on the
correct.
right hand side.
The scarecrow should be on the left hand side of the crow in order for the crow to move. Like I explained this at the very beginning. So
Okay.
how does the crow moves? So basically, what is the moving pattern of the crow? So this is what the moving pattern of the crow is. So suppose the crow stands here.
Mhm.
The crow looks at all the crow looks at all the scarecrows which are standing behind him. So it looks at all the scarecrows which are standing behind him. It looks at the nearest scarecrow which stands behind him. If the distance between them is less than k, so it jumps to the distance, it jumps to a distance k apart from the last scarecrow.
Okay, got it. Like yeah, get
Note
clear.
that it does not matter where the scarecrows are standing in front of him. So even if the crow is standing here and there exists a scarecrow which stands at a distance less than k here, it does not
Mm.
matter. The crow will not move, right?
Yeah,
In order for the crow to move, there should be some scarecrow standing behind him at a distance less than k.
right.
Okay, so think this problem as if all the scarecrows are boxes. So
Okay.
basically think that as if all scarecrows
Mm.
are boxes of size k.
So yeah, the scarecrow three wherever it stays, it does not matter, na. Like whether it stays at 5 or 4.5, it does
No,
not
it
matter.
matters. It matters. Why does it matter? Suppose the scarecrow 3 remains at 5. Okay.
Mm-hmm.
If the scarecrow 3 remains at 5, then what would happen? So then basically what did my crow did? So what was my setup? Okay. So basically there was my scarecrow 1, which was at
Mm.
0.5.
Yeah,
And now I have scarecrow 2, which is at 2.5.
yeah.
And now I have my crow here. So the crow
Is
stands
it
at
4.5?
4.5.
Okay.
And
So then,
suppose
okay, okay.
suppose my scarecrow 3, he is reluctant and he says that, okay, I will not move. Let me stand at 5.
Mm.
So now, in order for the crow to be thrown out of this x equal to 5, this scarecrow 2 has to start moving.
Okay.
And then this crow would also move. So it will take half more distance, right? It will take 0.5 seconds more time for the scarecrow 2 to reach 3 so that the crow reaches 5.
Right.
So if the scarecrow 3 does not behave cooperatively, then it would
Mm.
take 3 seconds for the crow to be thrown out of the field.
Right.
But if the scarecrow 3 is smart enough and he says that, okay, I will come to 4.5 beforehand, then it will take only 2.5 seconds for the crow to be thrown out of the field.
Right. Right.
So the scarecrow, you assume that the scarecrows are smart enough. They already know where to stand. Like
Yeah.
for this scarecrow 3, we did not initially know what scarecrow 3 will do. We first analyzed the initial situation. We realized that, okay, the crow jumps at 4.5. Then we say
Yeah.
that, okay, then why not make the scarecrow 3 come at 4.5?
Got it. Got it.
Hello.
Sir, please read my doubt in the chat.
Yeah, sure. Aditya says that what if we move the scarecrow from 2.5 to 3? Yeah, we can do that, but that would take 3 seconds and that would be more time than the minimum time required.
Sir, above one.
Uh, okay, can you tell me what did you mean? Like it would be
Sir, I
faster
mean,
probably.
sir, sir, the
Okay,
first scare.
so you
Yes,
suggested some way such that it takes 3 seconds, right?
yes, sir, yes, sir.
Yeah, that may be a completely valid way of doing it. But then out of all the valid ways which are possible, we need to output or take a way which gets the minimum time. So it may happen that t equal to 3 seconds is a valid way of throwing the crow out of the field. But then I have already shown you a way in which you can throw the crow out of the field in just 2.5 seconds, right? So if that is the case, we need to output the minimum time required to throw the crow out of the field. And that is the reason answer is 5 and not 6.
Okay, sir, got it, got it. Yes, sir.
Yeah, okay, great.
Hello, sir.
Yeah,
For suppose the Scarecrow 3 is not at 5 but at 8 or somewhere bigger number, then
exactly. Yeah.
won't we consider Scarecrow 2 to make the crow move forward?
Exactly, exactly. So if the Scarecrow 3 would have been some bigger number, say 8. So let me rub this down and say that okay, Scarecrow 3 is at 8. Then the optimal idea should be something like this only. This what should Scarecrow 3 do? It will obviously rush towards the crow because it wants to make the crow be thrown out of the field, right? But Scarecrow 2 also would also go in this direction so that the crow also keeps on moving in this direction. So depending on whether can the Scarecrow 3 reach the point where the crow needs to be jumped, the Scarecrow 2 makes a move. If I can move the Scarecrow 3 to if I had enough time that okay, Scarecrow 3 was initially at 5, I had enough time to keep it at 4.5, so I did not require Scarecrow 2. But if Scarecrow 3 was very far behind, then we would have not got enough time to reach to make the Scarecrow 3 come and stand at 4.5. And in that case, we had to move Scarecrow 2. This is something very similar to what we did here. Here, after the Scarecrow 1 reached 0, it had to, so after the Scarecrow 1 reached 0, remember that it had to move in the right direction, right? So that this crow moved here. So this is something very similar. Depending on what are the coordinates, the strategies may differ. Okay, let me explain the idea or how should the scarecrows move, and then probably it will be clear. So basically what I was saying is, this was what I had already written, that think all scarecrows as boxes of size k. So basically, suppose, so this is my crow and suppose this is at coordinate 0. Great. So now this is my first scarecrow. So this is my first scarecrow. What I request you to that you think that this is a box of size k. So think that okay, this is a box of size k. So now it first moves at this direction. So this is where my crow is. So it moves in this direction. It suppose this distance is d, then it takes d seconds to reach at 0. When it reaches at 0, so basically when it reaches at 0, you think it like this that okay, the crow moves out of the box. So as soon as the scarecrow one reaches 0, the crow goes here. This is something just like teleporting from t equal to 0 to t equal to k. I have imagined it as a box. Okay. Now, what should be the optimal idea of the other scarecrows? The other scarecrow would always love to stand at this position. Like this is always optimal. The other scarecrow knows that okay, that whenever this box will reach here, it will. So suppose there was one more scarecrow 2 here. Okay. Then Scarecrow 2 would always try to move to the right and reach at this position. Because it knows that if it can somehow reach at this position, then this Scarecrow 2 would also be a box of size k, right? So if it can somehow reach at this position, so as soon as this teleportation happens, because the crow will reach here and immediately, instantaneously, without wasting any extra time, it will go to this distance. So the optimal idea would be that you would always want the next scarecrow to stand at the first scarecrow's teleportation distance, basically. So let me show it using an example. Okay, so there are not very good examples here. We can have the last test case. So here it is. So we have 3, then we have an 8, 24, 25, 27, 29, 34, and 53. So you have a 20, just a second. Uh, okay, just give me a second. Probably I'm facing some issue with the pen. Give me a minute to fix it. Yeah, great. So this was the test case which we were discussing. 338, 24, 25, 27, 29, 34, and 53. So 338. Just give me a minute to fix it. Okay, so we were given a test case. It was 338, 24, 25, 27, 29, 34, and 53. 24, 25, 27, 29, 34, and 53. 29, 34, and 53. The value of K which is given is 12 and the value of L is 54. So the value of K is 12 and the value of L is 54. So the crow initially stands at at 0, right? So the crow initially stands at x equal to 0. So this is where the crow stands. So the first idea would be, so basically think as all scarecrows. So all scarecrows are boxes of size 12. So think of this scarecrow as this is a box of size 12. So what happens? It has 3 seconds to reach at this crow. Whenever it reaches here, the crow jumps and reaches 12. Okay, great. So whenever it reaches here, the crow jumps and reaches x equals 12. Now look at the next scarecrow. What will the next scarecrow try to do? The best way for the next scarecrow would be to somehow stand at 12, right? Because the next scarecrow knows that it would be best, because that I know that whenever this scarecrow reaches x equals 0, the crow will jump and teleport at 12. So it is best for me to stand at 12, because if I stand at 12, the crow will immediately see me and jump at t equal to 24, and that would be the best position for me, right? So this scarecrow will try to stand at 12, but it cannot do it. Why cannot it do it? Because there are 3 seconds it takes for the first scarecrow to reach x equal to 0, and the distance between them is 9. So this scarecrow will not be able to do it. But what will it do? It will do something like, it will just go as much distance far as possible. So basically it will go from 3 till 6, because in 3 seconds only that was possible. So it reaches 6 here. So if it reaches 6 here, when this crow reaches 12, basically it sees 8 here. So this effort does not actually count, because this effort does not actually count for the second scarecrow, as it would anyway see 8, and then it will move to a distance 8 plus 12, or 20. But I hope the essence is clear. Like, the essence is very simple. The essence is very simple, that I had a crow and then I had a scarecrow of length k, which actually forced the crow to stand here. Now, for all other scarecrows, and for the next scarecrow will try to stand here. But it may happen. So there are two things which are possible. First of all, that the next scarecrow has enough time. So suppose the next scarecrow had some initial position xi, and suppose it had enough time to reach here. If it had enough time to reach here, it will very smartly stand at this position, so that the crow can instantaneously jump to the next window or a distance of k. But if it cannot reach here, then what will it do? If it cannot reach here, then it will try to basically reach the closest distance as possible. So suppose this is where the next crow is, and suppose the scarecrow was standing somewhere here. So if the scarecrow was standing somewhere here, then it will try to move some distance, and suppose it reaches here. This may be a case, or there may be a case that okay, the scarecrow was standing somewhere very far apart, and it did not get enough time to stand here. So in that case, it goes here, and it reaches here. So these are the two cases where the next scarecrow could be the left or the right of the actual destination. If the scarecrow is actually right to the actual destination, what can it do? It can basically, then the previous scarecrow and this scarecrow will both try to contract the crow and will try to throw it out of the case. So basically, this is what we saw in the dry run, that what actually happens is that the next scarecrow and this scarecrow both try to move towards the crow. So in minimum time, the crow actually jumps and reaches the teleportation. And if this happens, that the scarecrow is on the left side of the crow, then it basically jumps a distance of k. Let me show you the code, and then we will probably have a dry run on it for a better understanding. So this is the code. Okay, so we take n, k, and l as input. After that, I have multiplied the values of k, l, and all values of ai by 2. This was just to ensure that the answer remains as integer, because we had to anyway report 2 times the answer in our case. So we have multiplied everything by 2 so that the answer remains finally an integer and we do not need to worry about it. So it was for that part. Now what we have a variable time which indicates what is the time, or basically what is the time which we have in our hand. So basically all this, what is the time the scarecrows have so that it can move. Then we have pos, which represents the position of the crow. And then we have PTR, which represents which index or which scarecrow we are handling now. Initially, what do we do? Initially, the first scarecrow reaches t equals 0. So that takes a0 amount of time. As after that, a0 becomes 0 because the first scarecrow has reached 0. The position of the crow has become k because now it has reached k. And the value of the PTR becomes 1. That means we start processing the next. We basically start processing the next scarecrow. Now look at this part. We run a while loop till pos is less than L and PTR is less than N. So if PTR is not less than N, that means all scarecrows had been already processed and we stop processing the while loop. And if pos is less than L, that means the crow has, and if pos is greater than equal to L, that means the crow has already reached x equal to L and we stop. Now look what pos is here. Pos is basically, we have already processed till PTR minus 1, right? So when we processed PTR minus 1, pos is basically a PTR minus 1 plus k. Because this was something like, so this was something like, that this was my this was my scarecrow. My scarecrow was standing at a PTR minus 1. And this is my value of pos. Basically, the crow has teleported to a distance which is greater than k from a PTR minus 1. So this is something which remains invariant in my code, that pos is a PTR minus 1 minus plus k. Okay, great. Now, there are two cases. If we see that absolute value of a PTR minus pos is less than equal to time, that means the scarecrow at the PTR position can actually reach pos within time. In that case, what do? We simply say that, okay, a PTR is then pos, right? Because we basically say that, okay, the scarecrow reaches that position. Apart from that, if I see that the value of a PTR is less than equal to pos and it did not had enough time to reach there, we basically increase the value of a PTR by time Basically, for that time, it moves towards that position. And then we say that, okay, pos is a PTR plus k. So basically, the crow jumps from that step to the next step, and then we start processing the next scarecrow. Apart from that, if APTR is greater than pos, that means the scarecrow is the right side of the crow, then we decrease the value of it by time. So basically means that for that time, the crow has moved to the left. After that, we find the distance, and then we increase the value of time as distance by 2. We have already seen that in the initial case. If you look at this case, the case which we discussed in the very beginning, yeah, here. If you look at that, the scarecrow 1 was standing at 0, and this was standing at 3, and the crow was standing at 2. So it took us half seconds, right? So this distance was 1, and it took us half seconds. So it takes half the time for both these scarecrows to contract the crow and make it jump to a farther distance. So that is what we have done. We have increased the time as distance by 2 because that is the more time we will take. And then we simply set APTR minus equal to distance by 2 because that scarecrow has to move that distance to the left. And then this is the invariant which we already maintained, that passes APTR plus K. And then we keep on handling the next scarecrow. Okay. Apart from that, if we see that pos is less than L, so when can the while loop breaks? The while loop breaks if PTR becomes greater than equal to N or pos becomes greater than equal to L. So if PTR has become less than N, so that basically means that we have processed all other all the scarecrows, and the crow has still not been able to reach L. In that case, we just increase L minus pos to time, because that basically means, we have processed all the scarecrows. So here we have an x equal to L. We have already processed all the scarecrows, and suppose here is my crow. Here is my crow at x equal to pos. So since we have already processed all the scarecrows, what will the best happen? The last scarecrow will start moving towards the crow, and the crow will also move here. So the crow has to move this entire distance. So we'll take L minus pos more time in order to reach here. And that is the reason why we do time plus equal to L minus pos. Okay. So any doubts with this? Okay, so basically the idea is that you think that all scarecrows are basically boxes of size k. Okay. So basically, you think that whenever the crow sees a scarecrow, what does it does? So whenever the crow sees a scarecrow, what will it do? It will reach out. It will teleport a distance of k, right? So why not think about that? Okay, these scarecrows are boxes of size k, and whenever it reaches it, it actually goes to a distance greater than k. So this is something like that. Initially, the crow was at 0, and then there was this scarecrow, which was at some distance. It keeps on moving this distance, so it takes some time. So as it takes some time, it reaches here, and then by this time, the crow has moved out of this box at this position. Now, when it reaches this position, what does the other scarecrow do? So look at what does the other scarecrow do. So now, this is where it is. This is the first scarecrow, and then this is the position of the crow. There are few cases. The first case is that there is that by this time there is some scarecrow standing here, and suppose it cannot reach this position. It did not had enough time to do that. In that case, what do? We basically push these boxes. So I basically push this box to the right, and then I also push this box to the left. So if this distance was d, in basically d by 2 time, in just d by 2 time, this distance will end up being covered. And as soon as it gets covered, what will happen? This scarecrow has moved a d by 2 distance apart. So this Scarecrow has moved d by 2 distance to its left, and this crow then moves, then actually reaches outside the box at here. So this is what this part of my code does. If you see that, okay, APTR is greater than pos, so first of all, you make the Scarecrow move for the time amount of time. After that, you compute the distance between the crow and the Scarecrow, and then you add distance by 2 to the to time, because that is the time you will take. And then you know that, okay, during this time, this Scarecrow will move a distance by 2 to its left. So you decrease its coordinate by distance by 2. And then you set pos as APTR plus K, because now the Scarecrow had actually moved outside the box and reached K. So this was one case. One more case which I discussed here is, so if you look at this part, then this part is very simple. This part is something that it was something to the left of it. So basically, suppose I had a very large box, and suppose I have this box also. So it stands here. So there is one more Scarecrow standing here, and then there is one Scarecrow standing here. And suppose the crow is at this position. So now suppose the Scarecrow is standing here. So what will it do? It will just say, look at if this distance is less than K or not, and then will update its distance by K, right? So and as soon as it's updated its distance by K, so basically think about it like this, that okay, I had some box already here, and the crow basically came here. So it will immediately go out of the box, and we will take no extra time to do it. So basically, we do not add up any time. We just see that, okay, we set the value of position of the crow as APTR plus K, and we keep on handling the next Scarecrow. Okay, you are bringing back the Scarecrow from right to left to transport it to right. Doesn't it reduce the future opportunity to reduce the time? No, actually it does not, because whatever you actually need some Scarecrow to push it to the right, right? Like if you do not use the Scarecrow on the right to push this crow to the right, then basically it is something like this. So suppose I have one Scarecrow. So I have one Scarecrow at this position, SC1, and I have a crow in between. I have the crow in between. And then I have the Scarecrow here, the second Scarecrow here. So if this Scarecrow is reluctant that, okay, I will not move, then what do I need to do? Then basically this Scarecrow had actually moved all the distance. So if this distance is D, this Scarecrow would have to move D distance from here so that the crow reaches here. And then this crow will see that the second Scarecrow, and it will move to some distance D plus K, right? So it takes D time to reach this distance D plus K. So isn't it better to do something like this? Like that the second Scarecrow also moves during this time here. So in just D by 2 time, what happens? The crow sees that, okay, in just D by 2 time, the crow and the Scarecrow move. It has also moved the distance D by 2 here, and then it reaches to D by 2 plus K. So in just D by 2 time, it reaches D by 2 plus K. And here in D time, it reached D plus K. Note that after this D by 2 time, we can always push the Scarecrow, we push this Scarecrow to the right so that it covers an extra D by 2 distance in the remaining D by 2 time. So in the D time, it also reaches D plus K here. So that means if you push this Scarecrow to the left, it is not worse. In the same case, it makes exactly the same distance, and it could actually increase further scope of this crow getting pushed to the right. So is this clear? Like it is not worse. Okay, great. That was all from my side. Apart from this, I knew that I could not. Yeah, the links will be uploaded in the YouTube video description. You can see it. Apart from that, I know I could not give a formal solution of why the answer should be 0 for the third problem. I will try to think about it and write it in the comments. Apart from that, if you had any problem you faced or any suggestions to give, please fill the feedback form. Thanks. That was all from my side.